General relativity, step by step. We've been working with the linearized Einstein field equations, hoping to find gravitational waves. And in order to simplify them so that we can solve them, we needed to impose the Lorentz gauge condition. Oh, that's not it. The Lorentz gauge condition is di mu h bar mu nu equals 0. And we can do that by finding a suitable gauge transformation. And I was hoping to have another gauge transformation which didn't stuff up the Lorentz gauge that we set up so carefully. Okay, and we found one. We found this theta nu equals b nu times sine of k alpha x alpha. And this subsequent gauge transformation did not stuff up the Lorentz gauge. It didn't alter the Lorentz gauge. Okay, so how do we exploit this freedom? Well, let's just write down what happens. H bar mu nu goes to, with a gauge transformation based on theta. See if I can get this right. It went to what it was before, minus di mu upstairs theta nu minus di nu theta mu. And then because it was the trace, because of this bar basically, because it was the trace reversed, we had to add eta mu nu di, which way around was it? It was di alpha theta alpha. Okay, so what I'm going to do is to use this and see what happens. Well, let's just make a start. We now know that di mu theta, let's say nu, from the previous screencast, that equals, what did it equal? That equaled k mu b, oh, it's here it is, it's b nu times times, and then the sign turned into a cosine, didn't it? Cosine of k alpha x alpha. That's right, isn't it? Okay, now hopefully we'll be able to see what happens to h bar. So that equals h bar mu nu goes to, under gauge transformation theta, h bar mu nu minus, and I'm going to have to rewrite this guy here so that it's differentiated with respect to the downstairs coordinate. You see here it's upstairs, and I've got it downstairs here. So it's eta, let's say alpha mu will sum across a mu. No, we won't. We've got a mu and a nu here, so I can't use mu. I'll have to use pi, a nice distinctive letter. Di pi theta nu minus, and then we're going to do the same thing. I'll call it an alpha. It's not an alpha. This one here is a mu. I want to preserve that mu. Now we've got di. It's the same thing, but with mu and nu swapped over. Pi di pi theta mu plus eta mu nu di alpha theta alpha. That's nice. Right, now what happens to that? Well, we've already done most of the work here. We've already done most of the work. Sorry, my computer's glitching out. We've already done most of the work here. So that equals h bar mu nu minus eta, I'm just copying from here, mu pi, and then here we've got a k pi downstairs and a b nu upstairs times cos k alpha x alpha, that's that term there, minus eta nu pi k pi downstairs b mu upstairs cos k alpha x alpha. That looks like a multiply, doesn't it? Alpha plus eta mu nu. Now that makes me nervous because we've got a mu and a nu on the top, mu and a nu there, it's a mu and a mu there, times di alpha x alpha. So this term here is just k alpha b alpha cos k alpha x alpha. Oh, I've got too many alphas. I'll call this something else. I'll call that a pi. Right, what does that do? Well, we can recast our equations a little bit. If I talk about this thing here as being h bar mu nu, but tt for transverse traceless, which I'll introduce in a minute, times, and that thing equals by definition a dash mu nu times, let's just say cos x alpha. Why? Because I've got loads of cosine terms there. Then that tells me directly that a dash mu nu equals the old version mu nu minus k mu b nu, which is that term there. Yes, because it's summed over the pi's. Minus, is that a plus? No, that's a minus. K, it's the other way around, nu b mu plus eta mu nu times this term, k pi b pi. Aha. Okay, so let me summarize what I've done. We started with the gauge transformation based on theta, and I showed in the previous screencast that theta doesn't stuff up the Lorentz gauge, so we're free to use it. And the way we're going to use it is to simplify the A matrix. And the way we're going to simplify it is by adopting all these functions here, adopting all this simplification here, and it gives us this nice way of updating the A matrix. So what that says is that the gauge transformation theta modifies the A matrix. Remember that we've got h bar mu nu equals a mu nu e to the I. Actually, I'll use the sines and cosines. It actually started sine k alpha x alpha. Oh no, it was a cosine. It was cos, because it was cos plus sine, wasn't it? Oh. Let's just say cos of k alpha x alpha. And then what we had was a further gauge transformation of theta, where theta was this this transformation here. No, it wasn't. What was it? I won't be able to find it now. It was this one here, wasn't it? That one there. So we're going to apply that further gauge transformation, and that allows us to modify or permute or change or something A. And so that tells me that h bar mu nu in this new gauge, which is called TT for reasons I will talk about next, equals a dash mu nu cos of k alpha x alpha, where a dash is given by this equation here, which I'm going to write out again. A dash mu nu equals the old one minus k mu b nu minus k nu b mu, just copying from here, plus flat space metric. See how much effort and time the linearization makes, because rather than fooling around with a general metric tensor, which would be the devil's own job to deal with, I can just write a beautiful constant flat metric. Mu nu, what are they? K summed, B summed. There's just one little wrinkle on here. It's not really a wrinkle, but it's probably worth mentioning because it threw me off when I learned this stuff. I just want to let's go back to the transformation here. We've got theta nu as a gauge transformation equals b nu times sine of k alpha x alpha. I'll just pinch in on that and have a look at it. There's a little bit of a problem. Well, it's not a problem, but it looks like it might be a problem. This theta depends on k. And it looks like you're cheating. Because you say, well, hang on a minute, it depends on k, and I haven't finished fooling around with it. But there are two replies to that. The first one is, so what? It depends on k. I can choose my gauge transformations how I like. They can depend on the day of the week. They can depend upon anything. They can depend upon your astrological star chart. They can depend upon anything you like. And the fact that it depends on k, well, so what? I'm in charge. I can choose my gauge transformations as I like, and I may as well choose them to sort of coincide and co-align and help with the gravitational wave I'm trying to understand. Of course my coordinate transformation may be sensitive to the gravitational waves I'm looking at. Why not? The second answer is, I can't remember what the second answer is, but there's a second answer to this. Oh yes, the second answer is it doesn't matter. The reason that you might be suspicious of this transformation is a statistical reason. It looks like you're getting K to do two jobs. Number one, to specify the gravitational wave, and also, number two, to specify the coordinates. But that's okay. You can't do it in statistics. If I suddenly start to use coordinate axes that depend upon a random sample, then I'm in trouble, because it uses up a degree of freedom. But this is physics, not statistics. It doesn't matter. This is not a problem. Coordinate freedom is exactly what it says. Coordinate freedom is freedom. It is freedom to choose your coordinates, to choose coordinates to make your life easier, to make life easy. Here's me. Here's a black hole. I'm falling towards a black hole. I say, oh my goodness, I don't understand what's happening. Well, I'll just build an elevator around myself. And construct a coordinate system in here that I can fool around with. Nobody says, oh, hang on a minute, he's falling in an elevator and he's using coordinates specific to that elevator. Well, of course I am. Of course I'm using coordinates that make my life in this elevator simple. And I have got a gauge transformation here, theta, which I have chosen in the light of this gravitational wave to make my description of that gravitational wave easy. Although that simplification is not obvious at this point. Let me just go back to where it is. It actually looks like I've made it harder because I've got this matrix here and I'm subtracting and adding stuff from it. But we'll see in the next screencast that if I'm clever about how to choose B here, then I will be able to simplify my A matrix. And I'm going to stop there. Stop.